Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to module 1.4, and as you may recall, in the last module I introduced this concept of a dispersion relation. The idea is that, as you know, we are trying to write down this H matrix that we can use to model the channel, and if you have a uniform channel, uniform material, then corresponding to a particular matrix which is uniform, we can obtain a dispersion relation, this EK relation, and then you can adjust the elements of this matrix so that you get the dispersion relation that people believe in, from years of theory and experiment. And the example we went through was the simplest example, namely a 1D wire, where if you looked at the matrix, it would look tri-diagonal. What that means is, along the diagonal you have this epsilon, a number, then there's an upper diagonal which are t's, and the lower diagonal which are also denoted by t. And since it's uniform, these epsilons do not change, the t's do not change. And so if you looked at any row, it would look exactly the same pattern, t epsilon t. And so if you take this matrix equation and write it out, as you know, if you had a matrix equation with a 10 by 10 matrix, that's sort of equivalent to 10 algebraic equations. And one of those algebraic equations that you could write out would look something like this. E psi n, where n denotes a particular point on that lattice, is t psi n minus 1, the point on the left, epsilon psi n, that point, and t psi n plus 1 on the right. Okay. Now, and then last module I worked out how in a situation like this you could write the solution in the form of an exponential, e to the power I k n a, NA being the location of the nth point. That is, A is this distance between 2 points, between two atoms. Now, and substituting it in here, you get the dispersion relation. Now, what I want to do in this module is do this in a more general way. That is, here we took a very specific case, 1D wire, things just connected to the next one. And so we could write this out easily. Whereas what we want to do in this module and the next is do more complicated examples. You see, where writing everything out is a little more inconvenient. And so we need to get used to it and do it in a little more formal way. And the way it works would be that, you see, you could say that in general, we can write a matrix equation like that. If you wanted to write in terms of components, it would look something like this. E psi n is equal to h n m times psi m. So this m here, that's repeated, and usually the rule of matrix multiplication is that you sum over m. That means for a given n, what you do is you write hn1 psi 1 plus hn2 psi 2, etc. So that's what you denote by this summation sign in front. And this would be a general form of the equation, which in our special case becomes what we wrote before. Why is that? Well, because let's look at this, E psi n, and then I have to sum over m. What that means is, given any n, I should be changing m over all its allowed values. But then there are only 3 values of m for which this quantity is non-zero. And those 3 values are when m is right on n, that's the diagonal element, or if m is a 1 bigger or 1 smaller. And so, when I write out all the terms, the only non-zero terms would be 3 of them. The ones where m is equal to n, that's when I get an epsilon here because that's the diagonal element. When m is n minus 1, that's when I get the t. When m is n plus 1, that's when I get the t. Now the thing is, the convenience of this is, well, here it was only 3 things. But what if you had a model where it was not just tridiagonal, but there were more terms to it. Maybe even the next one is connected here, let's say. So it's not all zeros here, but there's a t prime there. Well, that's fine. This is still covered by this equation. We just have, when we write it out, instead of having just 3 terms, we might have 5 terms. There could be n plus 1, n plus 2, and there could be n minus 1, n minus 2. That's fine. So that way, this is more general, you see. Now, the principle, of course, is still the same, namely that as long as every row looks the same on this matrix, that is, no matter what n I look at, as long as every row is looking the same, the solutions can be written in the form of exponentials. And if I substitute this in here, what you'd get is, I guess psi n is this exponential, and times, I guess, some constant number you could put, psi 0. So if I substitute that in here, what I'd get is psi 0 e to the power I n k a. So I just substituted this in here, this side. And on this side, instead of psi m, I'll put e to the power I m k a times psi 0. So all I did is, instead of psi n, I put in this quantity. Instead of psi m, I put in that quantity. Okay. Now, you could write this in the form E, we get another pen, psi 0 is equal to and this exponential I can take over to the other side. That is, I could kind of multiply both sides with exponential minus I n k a so that it goes away from here and appears here. And then psi 0 being a number, I can just cancel out. And so I now have an expression for the EK relation. I mean, that's what we call the dispersion relation. Okay? And this would then be perfectly general. That is, no matter whether it's nearest neighbor, next nearest neighbor, doesn't matter. You could write E as equal to sum over M H and M e to the power I m minus n k a, and that's it. So how would you find the EK relation? Well, you just choose any point n. So, and that n is a point along this lattice. So you could choose any point, stand someplace, and then do this summation over all m. Okay? And of course, what allows you to write the answer so simply is because this is a uniform homogeneous material, so it doesn't matter what n you choose, you'll always get the same answer. So in this wire, you could stand here, do your summation, whatever you get, if you stand here and do your summation, you'll get exactly the same answer. So just choose one point, do the summation, and that will be the EK relationship. Now, this idea you could generalize a little bit. You could go to 2 dimensions or 3 dimensions. Let me explain. So supposing here, instead of just this one-dimensional wire, I actually have a 2-dimensional lattice. And for simplicity, I'll assume it's a square lattice, which means if the distance is a this way, it's also a this way. Same thing. That's not necessary, but I think we'll keep it that way. And let's say it's a nearest neighbor model, so that diagonal elements are epsilon, and the connection to the surroundings is t. Surroundings meaning the nearest neighbor. And it's nearest neighbor model. There's no direct connection to anything else. Now in this case, if we're actually trying to write down the matrix, it could take a little bit of discussion. But as I said, we don't really need to write down the matrix. We could just say the basic set of equations will simply look like the basic set of equations will simply look like what I had written before, namely E psi n is equal to sum over m h n m psi m. It's exactly the same. It's just that now when I stand at an n and I have to do the summation over m, it is not just 3 terms, it's more like 5 terms. Because if this is n, then when I sum over m, I'll have m could be right here, it could be to the left, could be to the right, could be upwards, or could be downwards. And if it was a 3-dimensional lattice, there could be another one in the perpendicular direction as well. Right? But basically then though, the equation still looks much the same, like what we had in the last module, or what I just started discussing in this module. Now the point is that now though, because we have a 2-dimensional thing, the solutions that we write would have this following form. Psi n is equal to psi 0 e to the power I k dot Rn. Rn being the location of the nth atom, this position vector. And this solution then, if we substitute it in here, we'd get the EK relation. So this is a generalization from last time. Last time we had a 1-dimensional problem, and so k was just a number. It had, that direction could be x, y, or z. Let's say it's x. Then what I really wrote as k could be viewed as kx. But now you see it's a xy plane. It's a 2-dimensional thing. K is a vector. It has an x component and a y component. Okay. Now, if I substitute this in here, what we'll get is, again, E psi 0 e to the power I k dot Rn is equal to sum over m h and m psi 0 e to the power I k dot Rm. That's it. And now I can cancel out the psi zeros from both sides, like before. And this exponential term I can take out from here and put the negative exponential on that side. So overall then, we immediately have this EK relation, which I can put up here. It will look like EK, and K is now a vector. It's a 2-dimensional vector. And if we're talking of a 3-dimensional solid, it would have been a 3-dimensional vector. And this is equal to sum over m h and m, and then e to the power I k dot Rm minus Rn. And so so given any solid, if I'm told these h and m's, then I can just start from here in this square lattice and immediately get the EK relations. So let's see what the EK relation then should be for the square lattice, the one that has these nearest neighbor couplings only. There's this epsilon on the diagonal and t corresponding to the nearest neighbors. So how would we sum this up? Well, you can see there should now be 5 terms. So when I write this out, I stand at any point right here, and then I'm moving the m along. So for m, if m happens to be right there, then h and m is epsilon. That's what I'll get. And then if m happens to be on the right or below or above or here, I'll have a t. So there'll be 4 terms which will have a t in there. So there'll be 4 of them. And each one of these, of course, will have a different phase factor, the one that comes from this term. And that's what we need to talk about, exactly what that is. So the first one, m is equal to n, and so Rm is equal to Rn, so the phase factor is just 1. So this is simple, there's nothing there. Now let's think about the next one. The next one, you see, we are talking about the one on the right-hand side from here. And if you think of, let's say, this is the point M, and this is the point N, and you want to know what is Rm minus Rn. Now the point is that supposing your origin is somewhere here, then Rm is that vector, Rn is that vector. What you can convince yourself is that when you look at Rm minus Rn, what you'd get would be actually the location of m. I guess I wrote this m and n wrongly. Let me turn this around. So this is n and this is m, let's say. So when I write Rm minus Rn, it is really just this vector. It is the vector that points from n towards m. Okay? So when we are doing this summation, and I'm standing at the location n, and I'm looking at that, it would be that vector which is in the x direction. So you'd have e to the power I k dot a times x. That's this one. Now if m happens to be in this direction, then again it will be exactly the same phase factor, but with a negative sign. Now if m, instead of being here, happens to be upward somewhere, then you'll have e to the power I k dot a y. Because now the vector running from n towards m, you note that this Rm minus Rn is a vector running from n towards m. And it really doesn't matter where your origin is. No matter where it is, it really just is that vector, you see. So it's k dot ay. And the last one will be e to the power minus I k dot ay. Okay. Now you can write this out. You'll get equal to epsilon plus t. You see, k dot x means actually the x component of k. So what you get is e to the power I kxa. And the next one is exactly the same, but with a minus sign. So you get t e to the power minus I kxa. And then here you'll get ky times a, and here you'll get minus ky times a. So it'll be plus t e to the power I kya plus t e to the power minus I kya. So if you had looked back at what we had done in the last module it was a 1D problem. And so you had 3 terms, this, this, and this. And now we have picked up 2 additional terms. These come from the y direction. And so the EK relationship now. So what you're writing down here is the dispersion relation E, and K is a vector, which means it has these 2 components, x and y, if you're working in the xy plane. And that's equal to then epsilon plus those 2 things I can combine and write as a cosine. So that will give me plus 2t cosine kxa. And those 2 again I can combine to write plus 2t cosine kya. And again, if you compare with what we had before, we had just the first 2 terms. Now we have the last one. And of course, the purpose of obtaining the dispersion relation in this context is because there is a particular energy momentum relation or EK relation that you believe in. and you're trying to adjust these parameters epsilon and t so that you get the right values. And the one you usually believe in, if it is this parabolic dispersion relation, what you want to do is make this look like some EC, some constant, plus h bar square over 2m times kx square plus ky square. If this is in 2 dimensions and there is an effective mass m, what you believe in is that the energy momentum relation looks something like this. And the question is, how do I make this look like that? And again, the basic principle is use that small kxa expansion. That is, the idea that cosine kx. So, you see, cosine of any small quantity can be written as 1 minus half x squared. And so, you could take this cosine and write it as 1 minus kx squared a squared over 2. And similarly, you could take that cosine and replace it with 1 minus kx squared a squared over 2. And now if you compare the two things, you see what you need to make them correspond. Namely, wait a second. Here I could write this as, if I collect these together, the epsilon plus 2t and another 2t here. So I'll get epsilon plus 4t. And then we'll have minus t times a squared times kx squared plus ky squared. So from the cosine, we have gone to this parabolic relation, and this is, of course, approximate for small kxa and kya. And this is what you can then compare to what you want. And that will then tell you how to choose your parameters. Namely, epsilon plus 4t should be EC, h bar squared 2m, that should be the minus ta squared. And if we just drop the ky, it's kind of like what we had before. But one additional thing that has come in now, you'll notice, is with 1d, this was epsilon plus 2t. Now we have 4t. Okay. So in the next module then, we'll go ahead and talk about one more generalization that is needed.